there is a stripe of dark clay running through the limestone at a cliff face in Stevens Klint, Denmark. It is roughly 1 centimeter thick. If you were standing there right now, looking at it without knowing what it was, you might walk past it entirely. You might assume it was just a variation in the rock, a thin layer of sediment from some unremarkable geological event millions of years ago. Above that stripe, 66 million years of everything that came after. Below it, a completely different world. A world that had non-avian dinosaurs in it. A world with 75% more species than the one we live in now. That centimeter of dark clay is the physical record of the worst single day in the history of complex life on Earth. And scientists just figured out, for the first time after more than 4 decades of trying, exactly what made it. The answer is so strange that it quietly broke a theory that has been standing since 1980. Here is the part that almost nobody is talking about. This is not just a story about identifying a rock. It is a story about realizing that the mechanism scientists thought killed the dinosaurs, the specific chain of chemical events they had been modeling, teaching, and building planetary defense strategies around for 40 years, was based on an asteroid that never actually existed. The rock they found is one of the rarest types of space object ever recovered on Earth, and its chemistry changes the entire picture of how 75% of all species on the planet died in what was effectively a single geological instant. If you want to understand what's actually happening at the edge of planetary science right now, this is where to start. Hit subscribe and turn on notifications. Every week we cover the discoveries that deserve a lot more attention than they're getting. SE section. What scientists thought they knew. The story of identifying the dinosaur-killing asteroid starts not at the impact site, but in a limestone quarry in Gubbio, Italy, in the 1970s. A geologist named Walter Alvarez was studying the KPG boundary, the geological line separating the Cretaceous period from the Paleogene, and noticed something odd. The layer of clay at that boundary contained iridium, a lot of it, far more than you'd expect to find in normal sedimentary rock. Iridium is vanishingly rare in Earth's crust. It sank into the planet's iron core billions of years ago when the Earth was still molten, but it's relatively common in asteroids, which never underwent that kind of differentiation. Walter brought the data to his father, Luis Alvarez, a physicist who had won the Nobel Prize in 1968, and together they ran the numbers. In 1980, they published a paper in Science arguing that the iridium spike at the KPG boundary was evidence of a massive asteroid impact. Their paper was controversial, immediately and intensely controversial. The dominant theory at the time was that the end Cretaceous extinction had been caused by gradual volcanic activity, specifically the Deccan Traps, a massive series of eruptions in what is now India that had been pumping gases into the atmosphere for hundreds of thousands of years. The Alvarez paper said no. It was fast. It was catastrophic. It was from space. Then, in 1991, geophysicists identified the buried Chicxulub crater in Mexico's Yucatan Peninsula, and the argument was essentially settled. The crater is roughly 180 kilometers wide, about the distance from London to Birmingham. It's buried under approximately 1 kilometer of limestone. At the surface, you can only trace its ring by following the arc of cenotes, those freshwater sinkholes the Yucatan is famous for, which formed as groundwater dissolved the fractured rock along the buried impact rim. The impactor itself was estimated to be somewhere between 10 and 15 kilometers across, roughly the size of a small city, and it struck at approximately 64,000 kilometers per hour. The energy released was billions of times greater than the largest nuclear weapon ever detonated, so the fact of the impact was established. A giant rock hit Earth 66 million years ago and ended the Cretaceous. What scientists didn't know, and what nobody had been able to pin down definitively, was what kind of rock it was. And they filled that gap with an assumption. The prevailing assumption was that the impactor was a CM-type carbonaceous chondrite. CM chondrites are one of the more common types of carbonaceous meteorite. They're relatively water-rich, they contain organic compounds, and crucially, they carry significant concentrations of sulfur. That assumption got built into everything. It went into the climate models. It went into the extinction mechanism. It got taught in universities. It became the foundation for 40 years of work on how exactly the impact killed so much, so fast. That assumption was wrong. What actually happened is that two separate research teams, working roughly 2 years apart, closed in on the truth using two different chemical fingerprints. And the convergence between them is what makes this so compelling. The first breakthrough came in August 2024. A team led by Mario Fischer-Gorde at the Institut für Geologie und Mineralogie at the University of Cologne published a ruthenium isotope analysis in the journal Science. Ruthenium is a platinum group element, rare, dense, not something you think about in everyday chemistry. But it has 7 stable isotopes, and the ratios of those isotopes differ measurably between objects that formed in different parts of the early solar system. Asteroids that formed close to the Sun have a different ruthenium fingerprint than asteroids that formed far out, beyond Jupiter, in the cold outer solar system. Fischer-Gode's team measured the ruthenium ratios in KPG boundary clay samples collected from sites in Denmark, Italy, and Spain. The signature matched carbonaceous chondrites, not silicate asteroids. Not a comet. A carbonaceous asteroid from beyond Jupiter's orbit. The asteroid versus comet debate, which had been quietly running in the background of impact science for years, was closed. But here's what that study couldn't do. Carbonaceous chondrites are a big family. There are CM types, CI types, CO types, CV types, CR types, and others. Each has a different chemistry, a different volatile content, a different sulfur load. The ruthenium study confirmed the family. It couldn't identify the specific member. Christian Kobrel at the University of Vienna, who co-authored that ruthenium paper, noted at the time that finer isotope measurements might one day allow scientists to narrow the identification down further to a specific subtype within the carbonaceous chondrite family. That follow-through arrived on July 17, 2026. Georgi Makatadze, a postdoctoral researcher at the Institut de Physique du Globe in Paris, one of the few institutions in the world with the instrumentation capable of this level of precision, led a team that had spent years collecting KPG boundary clay from those same European cliff faces and running high-precision nickel isotope measurements on them. Why nickel? Because nickel is more abundant in the KPG layer than ruthenium. More atoms to measure means more signal, which means tighter precision in the isotope ratio, which means a sharper identification. Makatadze worked alongside Frédéric Moynier at IPGP and with co-authors Philippe Claes from the Vrije Universiteit Brussels and Christian Kobrel from Vienna. Kobrel now appearing on both the ruthenium paper and the nickel paper, a continuity link across the entire 2-year investigative arc. Their paper published in Science Advances. Title: The Origin of Cretaceous, Paleogene Impactor Revealed by Nickel Isotopes. The nickel isotope ratios in the KPG clay matched one specific subclass of carbonaceous chondrites. CO chondrites. Carbonaceous chondrites of the Ornans class. Named after the town of Ornans in France, where the type specimen was first recovered in the 19th century. An identification that had been 66 million years in the making arrived in a journal on a Thursday morning in July 2026. And the science press barely blinked, which, honestly, should have been a much bigger story than it became. CO chondrites. Let that classification sit for a second, because the rarity here is not a minor detail, it's the whole point. Carbonaceous chondrites as a class make up only 5% of all meteorites recovered on Earth. 5%. Most meteorites that fall to Earth are ordinary chondrites, the kind you see in museum cases and educational displays. Carbonaceous types are already unusual. But CO chondrites aren't just a minority within that 5%. They're a fraction of a fraction. They barely show up in global meteorite collections. Dr. Phil Biter-Dodd. Philippe Claes, the Vrije Universiteit Brussels professor who co-authored the study and provided the most direct public statement on the findings, put it plainly in the official University of British Columbia release. Carbonaceous chondrites of the Ornans class are definitely not like the typical meteors you find in museum collections. What makes them chemically distinctive is that they're dry. Extremely dry compared to most meteorite types. Chondrites contain far less in the way of volatile elements, less carbon, less zinc, less water, and critically, far less sulfur than CM-type chondrites, which is what scientists had been assuming the impactor resembled for decades. CO chondrites are primitive in a very specific sense. They haven't melted. They haven't been altered by water or heat. They're essentially frozen, unprocessed debris from the disk of gas and dust that coalesced into the solar system 4.5 billion years ago. And they tend to come from the cold, distant regions of the solar system, the outer asteroid belt, the Kuiper belt, the regions beyond Jupiter where the sun's warmth barely reaches, and where material from the early solar system has been sitting largely undisturbed since the beginning. The exact origin of the Chicxulub impactor is still uncertain. The nickel data, combined with the 2024 ruthenium data, confirms an origin beyond Jupiter's orbit. But whether this object came from the far outer asteroid belt, or from the Kuiper belt, or from some other debris-rich region of the outer solar system, that question doesn't have a definitive answer yet. What it does have is direction. And Clays didn't understate the implication when he said, being impacted by such a rare distant projectile really underscores how unlucky the dinosaurs were. Something sent that rock inward. Some gravitational nudge, a close pass by Jupiter, a slow cascade of orbital interactions, a collision somewhere in the outer belt that changed its trajectory just enough. Sent a 10 to 15 kilometer chunk of ancient solar system material on a path that ended at the shallow tropical sea covering the Yucatan Peninsula 66 million years ago, traveling at 64,000 kilometers per hour. And it happened to be the rarest kind of carbonaceous rock that exists. But wait, because this is where the identification stops being interesting in a classification sense and starts being important in a way that changes everything scientists thought they understood about what happened next. For 40 years, the dominant explanation for how the impact killed so much so fast centered on sulfur. The logic was clean, and it made intuitive sense. The asteroid vaporizes on contact. The sulfur in the asteroid and the sulfur in the target rock, the sulfur-rich evaporite limestone of the Yucatan, gets thrown into the stratosphere as sulfur dioxide and sulfur trioxide. Those gases form sulfate aerosols. Sulfate aerosols are extremely efficient at reflecting incoming sunlight back into space. Global temperatures drop fast. Photosynthesis slows. Plant life collapses. Everything above the level of bacteria starts struggling within weeks. The food chain breaks from the bottom up. 75% of all species are gone within what, geologically speaking, is an eye blink. That was the model. It was specific, it was testable, it was taught in classrooms. University of Bristol researchers published work as recently as 2022 reinforcing the case for sulfur-driven cooling. The sulfur model wasn't a fringe idea. It was consensus. Now, a CO chondrite carries far less sulfur than a CM-type impactor. The prior models, built on the CM assumption, attributed roughly 40% of the sulfur released during the impact to the asteroid itself. A CO chondrite at the same size and velocity would have contributed only about half that amount. And this finding didn't arrive in isolation. Separately, a paper published in Nature Communications in January 2025, using a completely different methodology, measuring sulfur concentrations and isotopic compositions directly from the Chicxulub impact structure and from a set of terrestrial KPG boundary sites around the world, estimated the actual total sulfur released at the impact at approximately 67 gigatons. For context, previous numerical simulations had been predicting somewhere in the range of 300 to 500 gigatons. The empirical measurement came in at roughly 5 times lower than the model prediction. 5 times. That is not a rounding error. That is a structural problem with the model. 2 independent lines of evidence. The CO chondrite identification from one research group, the direct sulfur measurement from another, both pointing to the same conclusion. The sulfur impact winter story was built on numbers that were significantly overstated. Clays addressed this directly in the UBC press release, and his phrasing is worth quoting exactly. It doesn't alter our theory of what caused the extinction event, but it makes it less likely that sulfur contained in the impactor was the smoking gun. The fine debris thrown into the atmosphere would have been the primary factor. Fine debris, that's the revision. Not sulfur aerosols from the chemistry of the asteroid, just rock. Pulverized, vaporized, blasted into the upper atmosphere by the sheer mechanical violence of a 15-kilometer object hitting Earth at 64,000 kilometers per hour. Tiny silicate particles, fine dust suspended globally in the stratosphere, blocking incoming sunlight for what climate models suggest could have been years to decades. Photosynthesis doesn't stop because of a chemical reaction. It stops because the sky goes dark and stays dark. Plants die. Everything that eats plants dies. Everything that eats those animals dies. 75% of all species gone. Not because of what the asteroid was made of, because of how large it was and how fast it arrived. The chemistry of the rock turns out to have been almost beside the point. The scale of the violence was always going to be enough, regardless of the impactor's sulfur content. Now, the sulfur story hasn't been completely retired, and it's worth being precise about what the new findings actually change versus what they don't. The impactor was not the only source of sulfur at Chicxulub. The Yucatan Peninsula sits on thick beds of sulfur-rich evaporite rock, ancient layers of gypsum and anhydrite that had been accumulating on the seafloor for millions of years before the impact. When the asteroid struck, it vaporized those rocks too. The sulfur from the geology of the target site, independent of whatever the asteroid itself contained, was real and substantial. The University of Bristol team's 2022 argument that sulfur from the target rocks alone was sufficient to drive meaningful stratospheric cooling hasn't been falsified by the CO chondrite identification. It's just that the impactor's own contribution to that sulfur budget was smaller than the models assumed. The authors of the 2026 nickel paper are also careful to note that the nickel data cannot yet definitively distinguish CO chondrites from an even rarer class called CT chondrites. These are so rare they barely exist in any collection and haven't been studied in depth. The isotope signatures of CO and CT chondrites overlap enough that the current data can't fully separate them. The team is already planning future work using chromium isotopes, which may provide the sharper discriminating power needed to close that remaining ambiguity. So the identification, as strong as it is, sits with a narrow edge of uncertainty that the researchers are transparent about. But none of that changes the central shift. The sulfur from the rock was not the smoking gun. The fine debris was. And if that's correct, it changes the extinction narrative in a way that's both scientifically important and, if you sit with it, genuinely unsettling. Stop. Because what comes next isn't about 66 million years ago. Every consequence model for a future large asteroid impact, the frameworks that planetary defense scientists at JPL and ESA use to calculate what happens if a big rock hits Earth, includes the impactor's composition as a key variable. Different compositions produce different sulfur loads, different amounts of atmospheric dust, different climatic disruption timescales. Those models inform which deflection strategies make sense. They inform how long post-impact winters might last. They inform estimates for how many people might survive and where. They're not just academic exercises. They're the basis for actual planning. If those models have been calibrated to a CM-type impactor, sulfur-rich, relatively common, when the most catastrophic impact in the last 66 million years was actually a rare sulfur-poor CO chondrite, then the consequence estimates have been wrong in ways that matter for real planning decisions. A future CO-type impactor would inject less sulfur than the models predict. The sulfate aerosol phase of the impact winter would be shorter or less severe than the simulations assume. That sounds like good news. And in one narrow sense, it is. But the dust winter doesn't care what the rock is made of. A 10-kilometer CO chondrite striking Earth at 64,000 kilometers per hour still vaporizes billions of tons of surface rock, still throws fine silicate particles into the upper stratosphere, still blocks sunlight across the entire planet for years, still collapses photosynthesis. The killing mechanism is more fundamental than the chemistry. It's the energy of the impact itself, which is determined by size and velocity, not composition. The CO chondrite didn't spare the dinosaurs. It just didn't kill them with sulfur, the way we thought. It killed them with darkness. Makatadze and colleagues explicitly note in the paper that refining consequence models for future CO-type impactors is one of the direct applications of this work. The technique they developed, high-precision nickel isotope analysis of impact debris, can be applied to other ancient impact layers preserved in the geological record. There are impact signatures going back billions of years. Identifying the compositions of those earlier impactors could reveal patterns in which regions of the solar system have historically delivered objects to Earth, which in turn has implications for hazard assessment of current near-Earth object populations. This isn't theoretical. The Chicxulub study is a proof of concept for a methodology that can now be applied to impact events across the entire history of the planet. That stripe of dark clay at Stevens Klint in Denmark has been sitting in that cliff face for 66 million years. Rain, frost, biological activity, the slow creep of geological time, none of it washed the nickel isotope ratios out. The chemical fingerprint of the impactor was locked into those sediment grains at the moment of impact, distributed globally as the finest particles settled out of an atmosphere that had been saturated with pulverized rock, and preserved in clay layers that geologists can walk up to, put a finger on, and touch directly. Researchers collected those samples over multiple years from sites in Denmark, Spain, and Italy. The same cliff faces Fischer-Godet's team had used for the ruthenium study in 2024, and brought them to the mass spectrometers at the Institut de Physique du Globe in Paris, one of the few facilities in the world capable of the precision this measurement requires. The result is a paper that narrows the identity of the world's most consequential asteroid from carbonaceous chondrite family, all the way down to a specific, extraordinarily rare subclass. 2 years of follow-through on the ruthenium work. Samples from 3 countries, high-precision measurements at the limit of what current instrumentation can do. And the conclusion, a CO chondrite, possibly a CT. The chromium data will come next and it'll close, or, well, narrow, that remaining gap. What strikes you, if you sit with this long enough, is the sheer improbability of the whole thing. CO chondrites are so rare on Earth that most people who study meteorites professionally have never handled one. And the one that ended the reign of dinosaurs, that cleared the ecological stage for every mammal that has ever lived, including every human who has ever existed, came from the cold, distant outer solar system, from a region so far from Earth that objects there rarely make the inward journey. Something knocked it loose. Something set it on a path that took 66 million years to arrive in the fossil record as a centimeter of dark clay in a Danish cliff. And the team in Paris measured what's left of it in nickel atoms, the rarest kind of rock, the most extreme outcome in the history of complex life. And the killer wasn't its chemistry. It was the dust it made when it arrived. That's the story that got published on July 17, 2026 in Science Advances by Georgi Makatadze and his co-authors in Paris, Brussels, Vienna, and Vancouver. And it didn't get anywhere near the coverage it deserved. So, if you've got a theory on what actually killed the dinosaurs, or whether the wrong asteroid problem should change how we're building our planetary defense models, drop it in the comments. Genuinely want to know what people make of this one.